So, here's my first example. Y equals 2x cubed plus 5x squared minus 4x plus 3. And I prefer f of x, so you can put an f of x near there if you want to or not. But I just really like the notation of f prime of x as opposed to y prime. I think y prime looks like y to the first. So I kind of try to stay away from that a little bit. Okay, well, first thing we notice is, and I'm not giving you any directions, we're just going to talk through and name as much stuff as we can name on this, okay? So first thing I want to do is just look at the function itself and see if I can identify anything about it. You should know that it is a polynomial function, which means it's everywhere continuous, it's everywhere differentiable on the whole entire domain, which be all real numbers. There's no cusp to anything, there's no denominators to mess this up, there's no root symbols to mess it up. Everything's nice and smooth. We call a polynomial function a nice, neat, friendly function. Everywhere continuous, everywhere differentiable. I shouldn't run into any problems with this function. Okay, so let's go ahead and find our critical numbers. So we're going to take the first derivative, I'm going to call this f prime of x, 6x squared plus 10x minus 4. That's my first derivative. This first derivative is everywhere defined, which means we're not going to get any critical numbers because the first derivative is undefined. I could have, of course, written right next to this function that the original function was everywhere differentiable, but being that the first function is everywhere differentiable will mean that the first derivative is everywhere defined. So you've got to watch your wording there a little bit. So now I want to know where is the first derivative actually equal to 0. I'm going to factor out a 2 here to make my next step a little bit easier. This is 3x squared plus 5x and then minus 2. So I'm hoping that this factor is kind of nice for me. I'm looking at 3x and x. And the only way to make 2 is 2 and a 1, but I want a 5, so I probably want to connect the 2 and 3 to make a 6, minus 1, and I do believe those are your factors. So I have two critical numbers. One will be a 1/3. This will be a critical number. And the other one will be x equals -2. That should be a critical number as well. So let's see where we're going here. I have my critical numbers. I want to apply theorem 3.5, and then I'm going to apply the first derivative test. So we're going to do all kinds of good stuff. First thing we do is something really, really simple. We just put these critical numbers and any other points of discontinuity, any discontinuity that the original function might have had. In this case, I don't have any discontinuities. The function was everywhere continuous. Its derivative was everywhere defined. So I don't have to play with that. But the next example, I'll give you a discontinuity someplace. But right now, I don't have any discontinuities. I'm only going to build my intervals around those 2 points right there. But I'm going to give you a little bit of directions. I'm going to say build intervals around any discontinuities and any critical numbers. So, first thing we're going to do is just draw a number line. We're going to put negative infinity on one side of it, positive infinity on the other side. Even if you know negative infinity is over there and positive infinity is over there, you're going to put it down because it's going to help you make sure that you get your intervals proper. Okay, now, I don't need a 0. I don't want you to mark a 0. The minute you mark a 0, you're telling me that 0, x equals 0, would be a discontinuity in the original function or would be a critical number of the original function, and it's not. So please don't mark your 0. I think that's a big problem kids have. The minute they put a number line down, they want to mark the 0. Don't mark the 0. I don't need a bunch of tally marks to do this thing. I have 2 points, okay? One's obviously going to be on the left of the other. Which one's smaller? -2. Which one's bigger? 1/3. Now, when I put two critical numbers or points of discontinuity down on my number line, I want you to realize that I've actually separated my number line into this section, and this section. So I'm going to have 3 intervals, even though I only had 2 numbers to plot on my number line. I don't just get 2 intervals because I have 2 numbers. I get 3 intervals because I have 2 numbers. So I'm going to make a chart, and the first thing we're going to do is list our intervals. We're going to go from negative infinity all the way to -2. Then we're going to draw a vertical line, and then we're going to go from -2 all the way to 3. Then we're going to draw a vertical line, And then, oh, I don't mean 3, do I? I mean 1/3. You should catch me on that. Oh, there's no way I could hear you, even if you were saying it, so. From 1/3 to positive infinity. All right, so far so good. The next thing that goes in our chart is a test point. And the test point has got to be an x value that's actually within the interval itself. Now, I already know for a fact that if I am going to have a relative max or a relative min, those values have to occur at my critical numbers. However, just because I have critical numbers doesn't mean I have to have a max or a min at those critical numbers. We've talked about those true-false questions a few times in class. Again, if I have a max or min, it has to occur at a critical number. So, this right here, x equals -2, this is a critical number. X equals 1/3 is a critical number. Alrighty. And we're going to continue. Give me a test point somewhere between negative infinity and -2. And if you're saying -3, get used to saying -10, because I like my tens. Somewhere between -2 and 1/3. Yes, indeed. We pick a 0 as often as we can. And then somewhere between 1/3 and infinity, I'm going to go for my 10 again. Now, after you find that test point that you're playing with, and let's just make sure we're clear on something. This function, this original function up here, it can't turn around in any other places other than x equals -2 or x equals 1/3. It can't, because if it turned around, it would have another relative max or a relative min, and we know that all relative max and mins occur at critical numbers. So in here, I'm not going to have a relative max or min. I can only have one at -2 or at 1/3. I'm not going to have a relative max or min here. I'm not going to have a relative max and min here. Which means that this interval is going to be totally increasing, or totally decreasing, or totally constant. But it certainly is not going to go up and down, otherwise I would have another critical number within it. And I would have broken this interval up into 2 other intervals. So I can pick any test point I want. Whatever the result of this test point is the result of the entire interval. Same thing for the second interval and same thing for the third interval. We may all have different test points. But if you get in the habit of picking your -10 and your positive 10s and your 0s like I do, we'll all kind of be able to share our work together really nicely. Now I want to test that first derivative. And you know what? Instead of an x, I'll put test point. I'm going to take this test point and I'm going to apply it to the first derivative, or apply the first derivative function to it, however you'd like to look at it. Now I know this is the first derivative, just like you do. However, I like this first derivative better. I like the first derivative that's in factored form, because I don't really care what the answer is when I plug a -10 in here. I care about the sign of the answer. It doesn't matter to me whether it's a 42 or a 27 or a -86. It matters to me whether this answer would be positive or negative if I put a -10 in. So let's just start. This 2 is definitely positive. If I put a -10 in here and times it by 3 and subtracted 1, can you see that this whole factor would be a negative factor? 3 times -10, -30 minus 1, -31. Again, I don't care about the 31, I care about the negative. And if I put a -10 in here, -10 plus 2, can't you see that that would be a negative again? Yes, it's a -8, but it's negative, which is what I care most about. So the first factor is your 2, that's positive, times a negative, times a negative. And what I'd like you to do is this. Positive times a negative times a negative for each of your factors, so I can see exactly what you're doing. A positive times a negative is a positive. And positive numbers, mathematically, we say are greater than 0. Good. Let's see what's happening when you use 0 for the test point between -2 and 1/3. I'm going to put a 0 in. My first factor is positive. Put a 0 in here, I get -1, so that's a negative factor. Put a 0 in here, this is a positive factor. So when I use 0, a positive factor, a negative factor, and a positive factor. So I want a positive factor, a negative factor, and a positive factor. These factors multiply together to give me a negative result, and negatives are less than 0. Let's go for our test point. You might think it's probably automatically going to go the other way around because it's turning, turning, turning. Yeah, sometimes we get a little whoop-whoop thing going in there and we don't turn around. So we have to kind of be careful. Okay, so let's try the 10. Come over here. If I put a 10 here, there's nowhere to put a 10, so positive, positive, positive. So plus, plus, plus gives me plus, which is greater than 0. It did turn around. Sometimes you get lucky, sometimes you don't. What does that tell me about the original function itself? Not the derivative function, because I already know what the derivative function is doing. But if the derivative is positive, which means greater than 0, then the original function must be increasing. Means it's going that way. I don't know if it's concave up, concave down, linear, I don't know. But I'm just going to draw this symbol right here for increasing. The first derivative function is negative, which is less than 0. Tells me that the original function, f of x itself, is decreasing, going down. Okay, now this is your theorem 3.5 that leads you to take this step. Again, we have a first derivative is positive, therefore the function itself better be increasing, going back up. I like these arrows because it actually maps the cubic function. I can tell it starts low and ends high. I can tell things about it. But this is indeed the pattern or the flow of the original function. Okay, so we're going to answer a few questions. We're going to say, where is this function increasing? Where is this function decreasing? Does it have any relative max? Does it have any relative min? Those are the 4 things that we really get off this chart. So I think I will do this here. Where is f increasing? F increases anywhere we said it increased. So we wrote increasing here, and all I got to do is go up there and grab that interval. No graphing necessary. Increasing was there. Increasing's here also. I go up to the top and I copy that interval. 1/3 to infinity. Done with that question. Where's the function decreasing? The only place I said it was decreasing was right here at -2, 1/3. All right. Why is the function increasing? Because f prime was greater than 0. Why was the function decreasing? Because f prime was less than 0. All right. Do we have a relative max? And do we have any relative min? Okay, min. Let me see. What do we have? A relative max is going to occur when the function switches from increasing to decreasing, or when the first derivative changes from positive to negative. That's what our first derivative test says. We can use the first derivative to decide whether or not we have any relative max, relative min, or neither. Well, the first derivative changes sign from positive to negative, which means I'm going to have a relative max. Right there, at x equals -2, I have a relative max. Why? Because f prime switches or changes from what to what? From positive to negative. That's what I need to see. Do I have a relative min? Yes, I do, because I'm going down and back up. So I'm going to have a relative min right here at x equals 1/3. And why do I have that? Use your first derivative